Hello and good day. My name is Faisal from University Malaysia Terengganu, UMT. Today I'm going to talk about neuroevolutionary based autonomous hydrographic surveying boats. And as a summary, high accuracy autonomous boat is very important for routine sampling. In this presentation, the process of setting up an autonomous hydrographic surveying boat equipped with neuroevolutionary controllers shall be presented. The results shall compare the performance between human operator versus neuroevolutionary based control of the boat in completing highly nonlinear obstacle avoidance and track completion tasks. Safe, accurate, and predictable autonomous systems in marine vehicles are very important. An understanding of intelligent systems fitted inside the ship is critical to ensure an autonomous ship is safe to be operated. Although the use of artificial intelligence in the design of the road-based vehicle has arrived to the level of self-driving, there exists a significant gap within the research of autonomous ship to operate in restricted waters, like rivers and also ports. In this talk, we shall discuss the relevant works in the literature to set a preliminary guiding principle for the design of autonomous ship. We present a simple illustrative framework as a starting point for ship designers to begin working in a simulated environment, which can be used as a foundation before the physical autonomous ships are constructed and tested in real-world situations. The state-of-the-art simulation environment typically consists of 3D virtual environment. This virtual environment can represent river, terrain, surface vehicle with distance sensor. This surface vehicle shall be controlled by a neuroevolution based piloting system. But wait a minute, you ask, what is neuroevolution? Okay, neuroevolution in its simplest definition means artificial neural network plus evolutionary algorithms. Typically, artificial neural network are driven using backpropagation. However, in neuroevolution, we shall use evolution algorithm to find the optimum artificial neural network. The work of neuroevolution, typically called CNE or conventional neuroevolution, which use single population approach, single population EA or population GA, to arrive to the final weight and bias of the artificial neural network. In this work, two scenarios will be presented. Number one, navigation in restricted waters, and number two, obstacle avoidance of an autonomous ship. In this talk, we shall show that the resulting autonomous surface vehicle is also capable of performing obstacle avoidance in the test track, although not being trained to do so. It never seen the test track before. The work demonstrated in this presentation is useful for the ship designers and can be extended for scenario-based planning for autonomous ship design. Fundamentally, an autonomous boat or autonomous surface vehicle is a subclass of mobile robots. Conceptually, mobile robots consist of control system, sensors like distance sensors, vision sensors, and also actuators like motors or servos or engines to respond to its surrounding. An autonomous mobile robot can sense its surrounding and act upon its surrounding based on its mission definition. In the field of maritime technology, there are vast potential of the use case of autonomous surface vehicle robots. The primary mission might be reconnaissance, patrol, intercept, or even environmental monitoring. But several common themes remain, such as maneuvering, cruise control, and also obstacle avoidance. Autonomous control of a surface vehicle is designed where an agent demonstrates river navigation while avoiding the obstacles in dynamic environment. It uses artificial neural network, as shown in the figure. The desirable steering and throttle control are achieved using ANN, which the weight and biases of the ANN are found using the unsupervised machine learning method. The unsupervised machine learning method used in this presentation is basically reinforcement learning, in which an agent is rewarded based on the attainment of accumulated checkpoints number in the simulation run. This is achieved using genetic algorithm, in which for every simulation run, the best design shall be retained to evolve in search for the best design until an arbitrary generation number achieved. It can be 100 generation, it can be 50 generation, as long as it's managed to obtain the most optimum neural network that capable to avoid obstacle or maneuver autonomously. So we need to answer, where are we now? Neuroevolutionary based work in the literature concerning ship steering or piloting remains lacking as compared to the autonomous cars. This is due to the high volume of production of cars compared to the ships within the consumer markets, based on the keyword search and also review articles on autonomous cars versus autonomous ship. A stark differences, which is up to 50% of difference in terms of volumes of literature, can be seen, which is shown in the figure. Such preliminary research has demonstrated a considerable amount of research gap within this discipline and require attention as the industry is moving towards fourth industrial revolution. One of the challenging aspects of control system development in marine discipline is the highly non-linear motion of ships compared to the road-based vehicle. In the work of Noor Shari, in 2019, the team demonstrated the use of artificial intelligence to steer ships in completing maneuvering tasks autonomously. A hybrid fuzzy logic and ANN to perform autopilot ship navigation was demonstrated by the work of Lee in 2013, while Moreira and Soares proposed the use of recursive neural network to perform tactical circles and also zigzag motions. An innovative offshore autonomous rescue vessel was introduced by the work of Kurowski in 2012 and also 2014 to assist large ships in search and rescue mission. So this proved that the use of artificial neural network to assist in autonomous vehicles, especially ships, has been demonstrated up until recently. So it's very popular. And in the view of visual perception, okay, which is something that commonly being applied in automobile discipline, we can see that in 2019, Liu and his team analyzed 4 artificial intelligence algorithms and deep learning frameworks in case of object detection and tracking, namely the KNN, very popular, K nearest neighbor, artificial neural network ANN, CNN, convolutional neural network, and also DNN, deep convolutional neural network. In view of automatic ship navigation system with collision and avoidance, Zhu and his team in 2011 proposed the use of potential field method in terms of its effectiveness and practical application. Convention of the International Regulation for Preventing Collision at Sea. In short, we call it COLREX. This is essential to apply for the manned and also unmanned vessel. So COLREX typically being applied for humans that operate the ship. But if you are creating autonomous ship, COLREX also need to be adhered. Okay, to comply with COLREX rules, Naim and his team in 2016 presented the application of neuroevolutionary methods in vessel overtaking, vessel head-on, and vessel crossing scenarios using artificial potential field (APF). However, in 2018, Pereira argued that COLREX regulation might fail in some instances where both the ships decide to take the same decision, which may lead to ship collision. So both ships are AI, and both ships are interpreting its position and try to save itself. It might collide. So Lecky reiterated in 2019 that any two vessels employing neuroevolution, number one, should not be overtaking when there exists a crossing vessel. Okay. Number two, an overtaking can be done by a faster vessel when there are no crossing vessel in the area of proximity. Complete collision avoidance system should consider certain factors such as ship types, traffic status, weather, and also navigation technologies. Therefore, to improve the collision avoidance system, Chang and Zhang in 2018 proposed the reward function as a main component of concise deep reinforcement learning, obstacle avoidance, to act as a feedback data to the system that evaluate the system performance of the control behavior at one scalar signal. Kozichenko in 2018 proposed the dynamic predictive guidance technique to address collision avoidance. It is agreed upon that collision avoidance should meet the following optimal rules: collision avoidance safety and network availability, and also the shortest navigation distance during collision avoidance. Now we move on to the methods. So the basic concept of GA or generative algorithm shall be discussed, followed by the description of agents, which is autonomous surface vehicle, ASV, and finally the description of the training track and also the testing track incorporated in this work. Okay, let me define what is GA in the context of artificial neural network. Okay, an artificial neural network is considered as an individual in the GA framework, in the generative algorithm framework. So if we have 40 number of population, so we have 40 numbers of neural networks. That's number one. Each ANN, okay, can vary in terms of its structure. Okay, the structure can vary. So for example, you have input of 2 hidden layers, you have 5 output layers, you have 2. So that can differ. Typically, we fix the number of inputs and fix the number of outputs. However, in the middle, the hidden layers can differ. Okay, so this is typical for neuroevolution. The set weight, okay, inside the fixed structure of ANN are evolved using GA in this work. So we are not going to change the structure. We are going to maintain the number of hidden layers and also the number of neurons inside the hidden layers. So we are going to only play around with the weights and also biases. Okay, that's number one. That kind of environment can be used as a platform to investigate the response of the agent can be set up in two ways, whether in a physical environment or virtual simulations. In physical environments, it's going to be very, very costly because in GA, you're going to use a lot of populations. So per population might be 40 number of individuals. So you need to have 40 numbers of machines or ships. Therefore, the best way is to get mathematical model and then define it inside the 3D environmental framework. And for each machine or each ASV, we call it an agent. Okay, so here we model the velocity of the agent, the hydrostatic and also the hydrodynamic performance, the distance to the target, and also the current position of the agent. So we use all this information inside for the objective function and also variables and also the constraint. And all this data that we get, how far we are from the objective function, either we are trying to maximize the number of checkpoints, having the agent to die when it hits the collider, okay, hits the terrain or other objects. And based on this data, we try to use the best agent that we have in that particular population to the next generation of the population. The pseudocode of the CNE or conventional neuroevolution is presented in the algorithm. In this case study, the structure of ANN, like I said just now, is fixed with the size of 10 neurons, why 10? Because we have 9 distance sensor input and 1 velocity input to be considered in the neural network. We have hidden layer of 3 neurons, okay, very small because CNE is very, very efficient, and output layer with the size of 2 neurons. Why 2 neurons? Because we have turning angle coefficient and also thruster coefficient. If you have 0 to 100 for the thruster value, so we use that, okay, instead of using the force that are going to be generated. This is going to mimic the real world because you as the ship operator, you're not going to say, oh, let's put out 35 kilonewton in this ship, okay, and turn left. No, we are going to instead push up the throttle up to few percentage. So that's the reality. So this is going to be used for the artificial neural network as well. Okay, now we are going to assign each of the agent with all the weightage, okay, and biases. Upon receiving the neurons, the agent will complete its task to maximize the number of checkpoints. So this is the award or the reward by the autonomous piloting itself. And since we are going to use reinforcement learning, so the first one is the reward to survive on the next generation if the agent get the maximum number of checkpoints, and the agents will be penalized or die if collided to the riverbank, okay, or if the agent hits another vehicle, okay. Okay, so the following generation shall continue where the offspring are generated from the best agent from the previous generation until the stopping criteria or the numbers of generation of the genetic algorithm is achieved. So these experiments can be described as a very non-linear constraint optimization as explained in the slide. So we have the objective function, which is the maximization of the number of checkpoints. So we have f that has 10 input variables, the number of sensors and also velocity, where variable x1 to x9 is the array of the distance measured from the riverbank to the body of the ASV. It can be riverbank, it can be obstacles. And variable x10 is the velocity of the ASV during the time of measurement. Each number of population shall aim to maximize the number of checkpoint gained given the prescribed time in seconds. So we have, for example, for a small experiment, we can give about 60 seconds, see how much checkpoint that the agent can obtain, okay? Now, let's put a constraint. A Boolean data of 0 to 1 is used as a constraint. So it's either you survive or you die, okay? If you touch the riverbank or any floating object, you're going to die. If the body of the ship collided, the Boolean set to 1, okay, and we say this is going to be unfit and discarded from the remaining population of the agents. Where if the Boolean is 0, so which means that the agent is fit, so this fitness shall be recorded and brought forward for the evaluation for the next run. Now I shall describe the agent. So I just described the setting for the brain or the AI. Now I'm going to describe the agent. The ASV is basically a sub-classification of autonomous mobile robot which operate on the water surface. In this work, ASV is modeled using typical dimension of a working class hydrographic surveying ASV available in the market is going to be a small one. And the detail is shown in figure 3 and detail in table 1 here. And in this work, the ASV is equipped with an array of 9 distance sensors with an interval of 20 located from the perpendicular to port side of the starboard, okay, as shown in the figure. In the simulation shall be conducted inside the simulation environment, okay, and the ASV shall only rely on the input gathered from the distance sensor and its velocity to decide its value of the thruster coefficient and also the rudder angle coefficient. Okay, now I shall describe the training tracks. The training tracks incorporated in the simulation is designed to mimic a very tight and challenging restricted water scenario is shown in the figure. The training track consists of several characteristics. In this training track, we have one straight cruise, so that the ASV shall have the chance to put 100% throttle and move forward. And this test track will have, the training track will have 4 sharp U-turns, 1 sharp 90-degree corner, and the width of the riverbank is 10 meters. So now we have a very small ship. The width or the beam is 1 meter, so it's 10 times from the size of the beam of the ship. And the dimension of the training track is 60 meter width, okay, the dimension of the training track, and 100 meter length, okay. So it's a very small dedicated training track just to train the autonomous vehicle. The testing track incorporated in the simulation is a larger restricted water. So It is fair if the training track to be small and very very complicated. Okay, in real situation, the testing track might not be as hard as the training track. The track will be larger. The track will have less number of obstacles, but it has real obstacles. Okay, and in the larger water environment, okay, we have an inland water transport scenario, surrounded by typical objects in ports like buildings, boats, weather, buoys, and also deck. Okay, of course, building will not going to affect on the neuroevolution because neuroevolution only concerned about its proximity. Okay, building is so far away. However, the boats, weather buoys, and also deck we're going to make this hard for the ASV. So let's describe the testing track. Okay, the testing track has 3 straight cruises, and six sharp U-turns, and we have 2 sharp 90-degree corners. The width of the riverbank is a bit larger, which is 20 meter, and also the dimension of the train track is 130 meter width and 140 meter length. Now let's go to the results. The autonomous maneuver of the ASV within the training track is shown. It can be observed that the ASV was able to negotiate turns successfully using CNE based ANN. With respect to the maneuvering characteristic, 3 sharp corners maneuver on the northeast of the training track is highlighted in the figure, together with its respective zone 1, 2, and 3. As the ASV cruising from the bottom right, okay, the southwest of the training track, it can be understood that the positive angle values of the rudder angle that represent the right turn, while the negative rudder angle value represent the left turn. In this experiment, the ASV cruise, assisted by the distance sensor, the ANN model evaluated the sensor input to produce the best throttle percentage and the best rudder angle values, as shown in the figure. It can be observed in figure 8, as the ASV enters zone 1, the rudder tends to turn the ASV to the right to follow the U-turn curve of to the right. The same pattern can be observed in zone 3. While maneuvering against zone 2, the ASV heads to the left to comply with the U-turn. In all 3 zones, it can be observed that the throttle and velocity value spikes ups and downs significantly each time aggressive maneuver is being executed, which is something that we desire for the CNE based ANN model. So we desire for this kind of response, saying that our artificial neural network is efficiently responding to the inputs. However, in real life, you wouldn't want to have your autonomous vehicle to move erratically. So you have to desire for a much smoother handling. So this is something that can be proposed for the future work after this. In the second experiment, which is for the testing track. Okay, just now we have discussed about the training track, so we see all those positive results from there. Okay, and in the second experiment, the same ANN model that we obtained from the first experiment is being used to investigate the capability of the model, the ANN model, to generalize the maneuvering characteristics in an unfamiliar surrounding using a test track. So we see this is a top view depicting the successful autonomous maneuver of the ASV using the ANN model. In this section, an additional challenge, the training track is incorporated, where 6 weather buoys were located in the U-turns and sharp turns, together with 2 boats and 1 deck situated on the northeast of the training track. So here we show 2 zones. Okay, zone number 1 is for the boats and the deck obstacle, while zone 2 is for the weather buoy obstacle. So we can observe that within both zones, 2 quick maneuver to the right were observed, where the NN is preventing the ASV from colliding the boats with the boats and weather buoys by performing quick rudder turn to the negative angle. It can be observed that the throttle and velocity values significantly dropped each time an aggressive maneuver is being executed. So it slowed down while evading the obstacle. And we see that the ASV is experiencing steady control of the rudder and speed in between the two zones, depicting that no unsteady maneuver is being performed in a straight direction cruise. So if you're moving straight, so we are not expecting any erratic movement, so which is good, okay, something that we desire very, very much. Now, to discuss a little bit on the results, okay, we try to compare the handling characteristics between human and also autonomous system. So we record it ourselves if we are the one who drive the ship or the autonomous ship, okay, and try to compare. We have shown that the ASV is capable of performing safe autonomous cruising while at the same time avoiding obstacles. Such finding can be further strengthened with the observation that the ASV is competent to perform safe navigation in unfamiliar setting. So we use the second track, okay, for the unfamiliar setting. While such capability is desirable in the realm of control, it can be hypothesized that such ASV is capable of performing better than human operator. Okay, we take into account that the ASV is equipped with 9 distance sensor. Now we try to use the human control data that control the vessel navigating in train track to compare the efficiency of the autonomous system between human and ASV. So looking at the figure, a 50-meter straight line cruising operation was captured for 10 seconds are compared between the human operator and the ASV. It can be observed that a human operator who relies on visual perception are more relaxed, okay, in the handling of the boats, okay, during the straight line and course keeping operation. Whereas for the straight line operation, okay, for the autonomous system that equipped with the distance sensor, the ASV has the tendency to perform abrupt obstacle avoidance, okay. So this is going to sacrifice the comfort of the passenger. Here, a 90-degree maneuver performance comparison between human operator and the ASV is shown. We observe that the vessel has made 90-degree turn, which is positive angle. The human operator carefully adjusted the response of the rudder accordingly, so it resulted in a more relaxed cornering maneuver. Okay, different than the ANN, it can't relax. Okay, during the cornering maneuver, the ANN seems to be very actively controlling its steering to maintain its distance to the riverbank distance, so the distance to the riverbank of the river. So it can't relax. So which is something that we don't want. If this is happen to be a passenger vessel, you're not going to be comfortable. Okay, but if it is for environmental measurement, then it's fine. So the comparative assessment discussed here between the human operator and also the autonomous system has raised a discussion in regard to the element of accuracy bias and comfort. So it's not going to be comfortable for the vessel handling. For human, the comfort factor in handling is very important to maintain longer endurance of work, which is different than autonomous system. We don't want endurance of human because you are not going to involve human in an autonomous driving system. So accuracy is much more important to reduce the probability of hitting an obstacle as trained in the experimental setup. Therefore, for the future work, it can be recommended that such an element of bias and comfort shall be included to serve as a potential work to be discussed in the future. For the conclusion, in this work, we presented the state-of-the-art review and experimental analysis using neuroevolutionary method in ship design discipline, which is quite rare. And we focus on the scope of autonomous handling scenario. Although autonomous vehicle has been progressing rapidly for the land-based vehicles, the research for self-driving in restricted waters like river and ports still possess a significant gap, despite of economic and also safety impacts. In this work, illustrative example has been presented using simplified ship model in rivers, okay, and we reveal that the preliminary neuroevolutionary model is not only good for navigation in the ports, but also capable for avoiding obstacles within the proximity of the distance sensor. Although we don't teach our ship to do obstacle avoidance, it managed to do it. So in this work, we used end-to-end, so which means that there is no interference in the middle by human. So this is what the ship has sensed using the sensor, train it, and this is the output. So no editing, no hard coding inside. So this is end-to-end reinforcement learning, unsupervised reinforcement learning. So the neural network can predict the best steering angle and also the best throttle response while avoiding collision with other floating objects and riverbank. Additionally, the handling performance of the ship has been compared between human operator and autonomous system. We may propose that the future work to consider the comfort factor in ship handling within the ANN training to ensure that the ASV is not only safe for maneuvering operation, but also has comfortable handling. So thank you so much for your attention and looking forward for the next meeting.